So now we're going to apply everything that we've learned. So I had a few misgivings yesterday when I was listening to you ask questions about that midpoint assessment, and everybody's struggling to remember that you have to do half reactions. Like, you have to look at the oxidizing, you have to look at the reducing, and you have to do the half reactions. This whole unit is based on half reactions. And then we go back to normal chemistry. But while you're in this unit, you have to look at it as an oxidizing half reaction and a reducing half reaction. Okay? And this is where we really see it come to play. So electrochemistry is converting chemical energy into electrical energy and converting electrical energy into chemical energy. First thing that we look at the easy one. We look at the Voltaic cell. The Voltaic cell is based on spontaneous reactions, which means what?
Happens with no energy input.
Right, so what has to happen? Oxidizing agent has to be higher than the reducing agent. Okay, if that doesn't happen, it's not a Voltaic cell because it's not spontaneous. Okay? So we're going to draw the picture out. And it takes all this space. There's lots of writing, so just giving you a heads up. Okay, so 2 beakers. So Voltaic cell has 2 compartments or 2 beakers. Okay, you have to see a division between 2. Typically, they're joined by what we call a salt bridge. And they're not usually this far apart. Salt bridges aren't this big. Okay, so this is what we call a salt bridge. And so a salt bridge typically is something that dissociates very easily. So what's an anion from the polyatomic group that dissociates with everything it binds with?
Ammonium.
An anion.
Oh.
But you're right, ammonium does.
Sulfate?
Nope, barium sulfate precipitates out very easily. Nitrate. So typically anything that bonds with nitrate. Okay? It could be any. It could be anyone. But we're also looking at cations that tend not to bind up. So like we wouldn't put silver nitrate here because if our solutions got chloride in them, we're going to precipitate out silver chloride. So potassium tends to form very little solids when they bind up. Okay? So we're going to put in a piece of metal here. And we're going to put in a piece of metal here. And we're going to have this build a solution. Okay? Now, we're talking about changes of energy, specifically chemical energy and electrical energy. We can measure that energy by connecting up a voltmeter. Okay? And it can be a voltmeter. They can show you as a box like this, so it looks like a battery. They can do it like this. They can do it any number of ways. So let's look at these different pieces of metal that we have. This one here, the most common ones that follow the same previous notes are zinc and copper. Okay, connected up to our voltmeter. Now we need to have some kind of solution that we put this in. And so what we see is that this solution here is going to have zinc 2 plus ions, and this solution here is going to have copper 2 plus ions. So when we look at our table, where do we find zinc and where do we find copper?
The midpoint.
Zinc is like down by the bottom, kind of like.
Yeah, zinc is at minus 0.76
And copper's at 0.34.
and copper's at plus 0.34. So when we look at copper and we look at zinc, which one is the reducing agent and which one is the oxidizing agent? This is a spontaneous reaction, remember.
Copper.
Copper.
Oxidizing agent.
This is the oxidizing agent. So that means that this is the reducing agent because it's spontaneous. Okay, it's really key that we remember that part. So if this is the oxidizing agent, that means that this is what we call the cathode. And if this is the reducing agent, this is what we call the anode. Because if you're the reducing agent, what kind of reaction is it?
Spontaneous.
No, there's only two to choose from. Oxidation or reduction.
Oxidation.
I didn't really do the question.
So the oxidation half reaction looks like this. Zinc is a solid. It's going to go into zinc 2 plus along with 2 electrons, right? Because it's a loss of electrons. It's going from a 0 to a 2 plus. So it must be losing electrons. But here, this is the reduction half reaction because it's an oxidizing agent. So it's going to go from copper 2 plus 2 electrons to copper as a solid. Okay? Does that make sense?
So
We're
for us to be
losing
able to-
electrons.
For us to be able to, like, if they just gave us like a question like that, just with the picture, we just need to realize that it's spontaneous and identify the oxidizing and reduction agent based on this like table then.
Yeah. If it tells you voltaic cell or it tells you spontaneous or it shows you a voltmeter instead of a battery pack,
Okay.
because we don't need to give this any energy, it's spontaneous, right? So if you get just a diagram like this where it's just a voltmeter and not a battery pack, or it has the words voltaic cell, or it says with the spontaneous reactions, then you know that you need to have you have to look at what your 2 electrodes are, what are the species that they are, which one ends up being the oxidizing agent, which one ends up being the reducing agent, and then you can figure out, going backwards, the half reactions. Okay, because the electrolytic cell requires electricity. We have to force that reaction to happen. Okay? So, what does this mean? This means that the zinc metal as the anode decomposes. So this metal is going to break down and the zinc 2 plus ions are going to increase in concentration. Okay? So if that's what we're saying over here, then what we say over here is that the copper 2 plus anions, they're not anions, they're cations, don't write anions. The copper 2 plus decreases in concentration, and copper metal is formed. Cathode builds in mass. Okay? So this is what you would physically see. You would physically see this electrode start to break down. You would see maybe it's a nice smooth surface and it starts getting very rough. There's decomposition. And this one here, if you were to take it out, dry it off and weigh it, you would have seen that the mass increased. So that the copper 2+ ions floating around in here are attaching to this metal. So if we have the anode and this is the cathode, this is where we draw on our physics knowledge, which way are the electrons flowing? Because there's, remember, chemical energy to electrical energy.
Negative to positive.
Negative to positive. Okay? So the electron flow is going to be this way. Whoops, my board's off. The electron flow is going to be this way. So that's really important that we know that part. Negative to positive. Okay. All right. So, definitions of the components that we're looking at. We have to have an anode where oxidation occurs. So that's what you need to, you don't need to know that it's the zinc or the copper. The anode is where oxidation occurs. The cathode is where the reduction occurs. So you need to connect those two pieces. So electrodes are usually metal conductors that carry electrons in and out of the cell. An electrolyte is a solution that contains the ions. So what's a solution that we could have for zinc? Zinc, is it soluble?
Zinc ammonium.
That's two cations together. You have to force that down.
Ooh, zinc nitrate.
Zinc nitrate.
I was gonna say
Okay?
that.
Copper nitrate. Anything that bonds with nitrate stays in solution. The one thing that I did forget to tell you back here though is this salt bridge here. You're going to have nitrate ions flow this way and potassium ions will flow this way. Okay? Alright, external current, a circuit outside the reaction vessel that allows electrons to flow. So this is your voltmeter that's allowing the passageway. And a salt bridge. It's a U-shaped tube that contains an electrolytic solution, otherwise known as a salt, that allows ions to flow between the beakers so that you can maintain the charge balance. Okay? But it keeps your reaction separate. It doesn't interfere. This is where we're always talking about spectator ions. This is where this comes into play. These are spectator ions. They don't react with the copper solution. They don't react with the zinc solution. They don't form any compounds or any precipitates in the bottom. The ions in the salt bridge. Okay? There are spectator ions. Metal that acts as a cathode is found in the half cell that contains the strongest oxidizing agent. The metal that acts as the anode has the strongest reducing agent. Okay? So this makes sure that it's spontaneous. So zinc, solid, is a strong reducing agent. So it's found at anode. And copper is a strong oxidizing agent, therefore it's found at the cathode. Okay? Another way to do this is to use a porous cup. And so you would have your electrode here. So this is the same beaker, two different electrodes. Only this part here is what we call a porous cup, and it's just a porcelain, I think is what they are. I'm trying to think of what crucibles are made out of. And our crucibles are made out of porcelain. So probably this is porcelain. I don't know, it could be any porous cup. And you stick the one electrode inside of it. Because we have to have that separation between the anode and the cathode in a voltaic cell. You have to have two distinct electrodes, okay? So this beaker is going to have copper 2 plus electrolytes in it, and this cup is going to have your zinc electrolytes inside of it. So your zinc ions. Okay? We're going to do this demo and the redox stoichiometry this week. I got the chemicals in yesterday. Okay? Probably Thursday or Friday. We'll see how far we get. See what we can knock off. Okay, so information pertaining to a voltaic cell is what we call cell notation. So all those numbers that you see on the side of your list there, we're going to start using those. So we can write out this half reaction. Every single vertical line, and you're going to see when we write it out, represents a phase boundary between the electrode and the solution in that half reaction. A double line separates the two reactions, the oxidation reaction from the half reaction. Okay, I'll show you what I'm talking about. So you have your anode, and then you have your electrolyte. Then you have this, which is your salt bridge or your porous cup. And then you have your electrolyte for your other reaction, and your anode. Okay?
Cathode? Or?
Yeah.
Oh, yes. Sorry. Good catch. Good job, Jaden. Okay, this part of the double line represents anion separation, and this part right here represents cation. So this is your nitrate flowing into your cell, and that other one was
Potassium.
okay. So your salt bridge where you have potassium nitrate, and we drew the little arrows where the nitrate moved out into the zinc side, and the potassium moved towards the cathode. That's what those double lines represent. So in our cell that we drew, we had zinc 2 plus, we had copper 2 plus, and we had copper as a solid. Zinc was which anode? It was zinc as a solid. Let's start this over. Zinc as a solid was which agent? The oxidizing agent or the reducing agent? Okay, so this was our reducing agent. And copper 2 plus was our oxidizing agent. Okay, so our reducing agent means that this was oxidation. And our oxidizing agent means that this was a reduction. Reducing agents are found at the anode, and oxidizing agents are found at the cathode. So once we identify that, we can write out our own cell notation. And it goes like this. It's going to go zinc solid, separated from the zinc 2+ ions by the salt bridge. Then we had copper 2+ with copper as the cathode. Okay, that's our cell notation. Now, it could be, you could also see it written with the spectator ions that they chose for their solution. In this particular example, we would write this: zinc solid, whatever solution we chose to use, we said nitrate. You could see it both ways. This is the more common way, just to write out the reaction, the half reactions themselves. But I have seen it written out with whatever solution they used. And you will see them pick sulfate because copper and zinc don't form a precipitate with sulfate. But if one of the electrodes was barium, you couldn't use sulfate. Okay? So let's try these 3 problems, and then when the bell goes, we'll start the second part. Okay?